All right, let's go ahead and take a look at section 8.1. Well, 8.1 deals with ANOVA, and what ANOVA is going to do is help us compare the means or the averages whenever we're dealing with a study that has more than two groups. So we can say that ANOVA is analysis of variance. And I'll talk a little bit about what do we mean analysis of variance. But I want you to know the main thing about this type of hypothesis test is when you're focusing on means and you're doing more than two groups. So, like a classic example might be if you're doing the average height for like high schoolers, that would be four groups: freshmen, sophomore, junior, seniors. Okay. Analysis of variance, again, just gets the short abbreviation of ANOVA. Now, when they talk about variance, okay, you're going to see some stuff here that's going to kind of feel like, oh my goodness, this is getting like way too technical for me. And it's actually, we're going to keep it very, very like low key. There is SSG, which is the amount of variance between groups. And then there's also SSE, which is the amount of variability that's within the groups, like some of the squares or the SS, like for errors. So I don't want you to be too concerned about memorizing what like SSG and SSE, like the abbreviations stand for, or even the whole idea of like sum of squares. I want you to keep more of a like general, like big picture idea about what those are. And so to help with that, and there's also formulas that are behind the scenes that Stackey is going to be doing to calculate SSG and SSE. And so we don't have to worry about that. Stackey will take care of it. So if there's any sort of like conceptual idea that I want you to have behind like what's SSG and SSE, well, just right here in this little pocket of white space, let's do like three little circles that are meant to represent like group one, group two, and group three, which is what section 8.1 is all about. If you have two or more groups and you're working with like averages and whether one of the averages is different than the other two groups. So when we talk first about SSE, that's talking about the variability like within each group. So let's say I've got this group here. Let's just think like test scores, where some people scored 90s and some people scored 80s, and then you also got some people have like 40s and 10s. Like the scores are all over the place. That's going to make it really difficult for identify like people in that group, what kind of scores they get. So that would be like SSE, like is all over the place. Like the variation is like just really scattered. That's going to make it really hard to again identify like who belongs to that group. Now, let's say I have another group here where everybody scored like 90s, right? Maybe an 89 is thrown in there, but everybody's like clumped together. That's a really, really small SSE. Like the sum of squares or they have it as the errors, right? The error sum of squares. That is a group that's going to be a lot easier to identify like who belongs to that group because they're so close together. They have a very small sum of squares for like the errors. Now, let's say this other group is just like so-so, right? They've got kind of stuff that's together, but it's these two up here that we're going to have probably the best time to like, especially this guy is going to give us the best opportunity to say like, yeah, one of these groups is not like the other groups. And so that would be like the distance between here and here. That is SSG, the variation between the groups. And so the best combination that you want is that you've got maybe one of your groups that has a very the variation within the groups is really really small, and that the SSG, the variation between the groups, is really wide. So like the groups feel like unique to themselves, but then also really distanced from each other. That's just my little picture that I came up with that maybe might help give the idea that what does it take for one group to feel like it's very like uniquely identified, but also very distant from the other groups. Now, it's really like a really combination of two things. We really want small SSE, like variability within groups, but then we really want a high amount of variability between the groups. And just heads up, I usually throw this on like the test as like a true false question. Yeah, you want a high amount of variability between the groups, which is this like those lines that I did. You want those to be as them to be as spread out as they possibly can be. All right. Now, things that you're going to need, just being practical here, you're going to need from here to here that on your reference sheet. So just make sure that you copy this to your reference sheet. Again, you can't have lecture notes during the test, but you can have your reference sheet, and you're going to need this. What is this? This is your ANOVA table. More specifically, it's how to go about like filling out an ANOVA table with each of its values that are like degrees of freedom. It's got the sum of squares. It's got the mean sum of squares, and then it's also got your F test statistic, which would be the value that we're going to use to get our p-value. Also note that there's two different degrees of freedom, one for the numerator. I put that right here. One for the numerator, a degree of freedom for the denominator. You'll also need to know how many groups there are, and we use K to identify as the way to denote that there's, 4 groups, 3 groups, 5 groups. Then we'll use N as a way to symbolize how many total cases there were if you put all the groups together. Now, we'll come back to using this in just a moment. I mean, I'll say a few other things. These are going to be provided by StatKey because they're very formula heavy based. And then what we'll do to get these two values is do averages. So we'll average these out. And then to get this final number, we'll do some division. Now, these right here are divisions. Division, division, division. And you'll see how those get used once we get into some actual examples. Now, the ANOVAs that are here, we've got, and give me just one quick second here. Yeah, the HO and the HA are going to be a lot like we did in the last section, 7.2, more like statements, sentences. Now, what the null is going to do is keep things real straightforward. It's going to say, nope, there's nothing different about the groups. Like all 3 groups have the exact same average, which again, if I was to do like height for like high schoolers, usually as you start off freshman year, right? As you go into sophomore year, you grow a little bit, junior year, and then by the time you get to senior year, that's probably when you're most of us like at our tallest. So we would probably expect there to be probably on the shorter side average for the freshmen, taller average for your seniors. But what the null is going to say is that nope, everybody's the same height. Everybody's got the same average height. But then what the alternative is going to do is say no, there's going to be a difference where the mean difference between at least 2 of the groups. There could be maybe a couple of them that are the same, but at least there's 2 that are going to be a distance of each other away from each other when we compare their averages. So let's go ahead and try this with a couple of examples today. And the first one here has to do with 3 different groups. It was an experiment regarding ants. And what they did was they did several different trials to see which type of food like food group the ants were more interested in. They had Vegemite, peanut butter, ham and pickles, and you can see that they did it 24 times, eight for each of the groups. So a couple things that we want to note here is K is equal to three groups of types of food, and then we've also got N is the 24 total like sample size when they put everybody together. Now, one of the things that you're going to be asked to do on the homework quiz test is just to make a general comment about the means. And usually what it's going to be is that the mean is not the same for all three of the groups. So as you look up here, this is the average number of ants that were interested in the Vegemite, like 30.8, peanut butter, a little bit higher, 34. Then you got the ham and pickles. So for whatever reason, it seemed like ham and pickles seemed to be the most favored, and we could say that because it had the highest mean. So just keep it really simple. You know, the first straight out observation when comparing the means is that the means differ. Then we can either say who's got the highest or the lowest. I'm just going to go with the highest, with one observation being that ham and pickles being most favored by ants. Now, for the null hypothesis, you can see here it says state the hypotheses. If we wish to conduct an analysis of variance, test to see, test whether there is a difference in the mean number of ants per snack based on the three food groups. And so the null is going to say, no, it doesn't matter what food group that you try to give the ants. They're going to love everything the same. So the way we'll write that is we're going to say mean number of ants. And you want to make sure that you specify this is a study about means, that the mean number of ants is the same for all three food groups. So when you write your HO, you want to mention, again, it's about a mean, what the variable is, which would be the number of ants, and then that there's three groups of what? In this way, it's three groups of food. And then for HA, it's always going to be the exact same thing for everything in section 8.1, that the mean differs between at least two food groups. And that's what I want you to use every time that you're working on something about ANOVA. The mean difference between at least two groups. So there might be a couple of groups that are the same, but again, there's going to be at least for sure two groups that when you compare them, that no, these are not, they don't have the same average. Now, I want to first do this example where there's nothing on the ANOVA for us, and it's going to be strictly something that we're going to rely on StatKey to do. Now, this study here, I might right now be using a slightly older version of this lecture note as opposed to the one that you have here. But there is one about ants and this food. And we're going to go to ANOVA for difference in means to go find it. And you're going to see that it's going to actually do all of this for us. And we're literally just going to be copying it. But it's really these right here, the sum of squares, that are very, very like difficult to do if we don't have a formula for it. And the formula itself is very busy. And so that's not something that we're going to busy ourselves with. We're going to let StatKey do the heavy lifting. So let's go over to StatKey. And you can see down at the bottom where it's got ANOVA for difference in means right there. And then when you get in here, there's going to be one at the very top that says brain size. And then we're looking for the one that's ant. And so this the lecture handout that you had might already um, have it already identified that it's the sandwich ants by filling. So we're going to click on that one. It's the only one about sandwich ants. I'm pretty sure it is. And you can see right here that it's got the data set that they mentioned to us. Remember, they did it 24 times, and the means were 30.8, 34, and 49.3. So this is the right data set that we need. And then to get the ANOVA table, you see the blue box right above. There it is, ANOVA table. And so once you click on that, I'm seeing where it popped up for me. There it is. Yeah, and for one of the homework assignments, you're literally just going to copy it. Yeah, the 2, the 21, the 23 are our degrees of freedom. And then you've got the sum of squares, the 1561, 2913, 4474. And we're just going to be, thank you, Stecky. Thank you, Stecky, for doing those formulas that we're glad that we're not having to wrestle with. Now, I'll talk a little bit more about these, but let's go ahead and just copy them in here. 2, 21, 23, 1561, 29, 13, 44, 74. Now, we are just going to go ahead and copy these, but let me also go ahead and make a few comments of what was some of what Stacky did to make some of these boxes. Now, these right here were formulas, right? And if you want to look up like the formula for these sum of squares, feel free to do it. But I want you to make a little note that this right here stands for mean. And so they're averaging something. What they're averaging is this. And I want you to put that in your calculator. Like, and what do I mean specifically? I want you to take 1561 and divide by 2. And you'll see that's how Stacky got this 170.5. Likewise here, if you take the 29, 13 and divide by 21, you'll see that's how Stacky got the 138.7. So what it's doing is it's doing the average amount of sum of squares between the groups, and the average sum of squares, the errors, like the sum of squares within the groups. And then lastly, we saw that Stacky had a 5.627. And the way that it did that, again, I want you to try it, was dividing these two. Like the 170.5 divided by the 138.7. And the reason why I'm doing this is to show you on the next example, it's going to be more on us to do some of these smaller little calculations. Now, what we're going to do next is get our p-value to see whether we can reject the idea that the average amount of ants for each group of food, reject the idea that it's the same for all three groups. Now, what you'll need is you'll need a degree of freedom, but you're going to need two of them. This is the degree of freedom for the numerator. This is the degree of freedom for the denominator. So it'll be 2 and 21. And then we'll need both of these and the F test statistic. Now, the F test statistic is a lot like what we've been using with like Z test statistics, T test statistics, the chi-squared statistic. All of those are just ways to see whether we have something that's extreme so that we get a small p-value. We can reject the null hypothesis. But let's go there. Let's go to what's going to be our last distribution for this class. So sad. I know we're getting to the very end here, huh? And let's go to stat key. And then you'll see it right there. There's the F distribution. Click on that. Degrees of freedom, we've got the 2 and we've got the 21. We're going to click OK. And like the chi-squared, it's also just right tail. And just like a lot of our distributions, it's going to have the p-value 0.025. Don't believe it. Down at the bottom where you see my 4.420, click on that. And that is where we want to put the 5.627 and click OK. And there's our p-value, 0.011. And same business as usual. If the p-value is small, smaller than our alpha, in this case, we're going to do a 5%, we're able to reject the null hypothesis and say that there is enough evidence. And again, just be sure that when you do this with your homework, you take screenshots of this and submit it with your homework to get your not lose any points. And then let's finish this guy out. We've got 0.011. That is smaller than a significance level of 5%. So we can reject the null hypothesis and say that there is enough evidence to support, or again, you can say to support or to suggest, either word works, that the mean number of ants differs between at least 2 food groups. And most likely it's because if you compare these two, that there's like these two are maybe not that far away from each other. The 30 and the 34, but definitely the 30 and the 49 being so far away from each other. I mean, there's an argument that was not a fluke. I mean, maybe ants just aren't that much into like vegetable stuff. They want their meat. All right, let's try one more. Now, what I want you to do first, I want you to read this one for yourself and real quick identify, what is K, what is N. And I want you to read the prompt just to get a real quick context for what this study's about. Okay. All right. So again, remember K is how many groups there are. And we can see right here that there are 4. There are 4 singing groups, and you can also see right here that although the sample size is not the same for all 4 groups, there was 130 total in the sample. Now, what they're going to do here is they want us to do a test to see whether the average height differs by voice. And you can see that there is a difference, right? If you're in the soprano group, the alto group tend to be on the shorter side, about 64 inches tall. And then you got tenor and bass that are about 5 inches taller, 69 and 70. And so what we're going to do, if we want to do a test, we're going to write an HO, write an HA. But heads up, this homework is going to want you to make just a brief, just general comment, like, is there a difference in the mean heights? Yes, the means do different. And then go ahead and just call somebody out, right? It does seem like either way you want to do it, that there is a difference with the soprano and alto being smaller, shorter, or the tenor and bass being taller. So let's go ahead and put just something real straightforward. The means differ with tenor / bass being Taller. Now the null is the one that's sort of like our Debbie Downer. Like, nah, there's really not going to be a difference. So it'll say, the average height is the same for all four voice groups. But then the alternative is going to come back and say the, or we could just say average height differs between at least two groups. Now, the reason why I'm doing a second example, one, because again, I want to make sure that before you leave this lecture that you feel pretty good, like as comfortable as you can with it, the procedure. But secondly, when it comes to the test, you will not be required to hop over to Stacky to go and grab any of this information. Now, in the homework, you will need to, specifically for this column there. That is the one that when you're doing sum of squares within the groups, sum of squares between the groups, it's those are more like time consuming formulas. So the way that it'll happen on the test is that two of them will already be given to you. All you'll need to do is fill in the gap, whatever's missing. Then you'll also on the test need to fill in the other pieces of information. Now, that is why I want you to have the ANOVA table on your reference sheet. When we're doing the degrees of freedom, this is what you need to know. That when you're doing the degrees of freedom for the groups, it's k minus 1, which k is how many groups there are, minus 1. And then the degrees of freedom for the errors is n minus k, which is your sample size minus however many groups there are. And then the bottom one will fill in. It's sample size minus 1. So let's do it. Now, on the homework, you don't need to put down, I'm doing it for the lecture notes. You just need to put the answer. So it'd be n, it's going to be for groups, it's k minus 1. I'm going to put it really tiny just for the notes. K minus 1, which right now it's 4 groups minus 1, which is 3. And then for the errors, it's n minus k. I'm just putting really small just for the lecture notes. So remember in this one, n, there it is at the top, was 130. So it'd be 130 minus k, which is 4 groups, which gives us 126. Now, once you know those, you know the last one. They should always add up, like vertically, 3 and 126 and 129. But if we also stick to just what the ANOVA table says to do, it's the 130 minus 1, which is 129. Again, it's a big deal. These add up vertically to give you the total degrees of freedom. Likewise here, Stacky has already given us 2 values to start with. So it should be that when you add up whatever's missing here with what's already given, it should be a total of 1854.9. So what I want you to do on your calculator to get this missing value is to just work backwards and do 1854.9 minus that smaller number on the top. And that's going to fill in the gap there. And so it should be 796.7. So again, the reason why I'm doing this example, one, to give us just a little bit more practice before you go off to go do this on your homework on your own, but also because the test, this is how it's going to be. 2 numbers will be given. You just got to do subtraction to fill in the blank. Now, the rest of this is going back to, remember when I showed you that those little fraction bars on the earlier ANOVA table? I said that those were divisions. Yeah, so there's Yeah, if we go back up to the ANOVA table, you can see there's little slashes. That's because there's divisions we're going to do. But the other thing that I mentioned just a moment ago is that the little M that is right here stands for mean. So what we're going to do is average these out. So you're going to take your 1058.2 and you're going to divide by 3. Now, you don't need to actually show me any work on your homework. I'm just doing it really small here so that, again, if anyone goes back to look at this and was like, wait, how did we get this? It's taking the 1058.2 divided by 3, and you're going to get 352.7. And then same thing here, average those out. So take the 796.7, divide by 126. 796.7 divided by 126. And you're going to get 6.32. Now, for these, when you're doing your homework, I mean, you're welcome to use however much I rounded. But if it doesn't say, I would just round to maybe one decimal place. And then for your finale to this, you're going to divide those. 352.7 divided by 6.32. I'm just going to put it right here just for the sake of the notes. And you're going to get 55.8. Now, the reason why we got such a huge F value is because of this, right? There was a high, like the 352, that's a really high amount of variance between the groups. But then the 6.32 is a low amount of variance within the groups. So this is like one of the best combinations ever. You remember the little true false question I'm going to throw out there is that you're definitely looking for a high amount of variability between the groups, which is the guy on the top. Now to end this thing, we're going to need degree of freedom 3 and degree of freedom 126 again for the numerator and the denominator, and then we'll also need the 55.8 right tell it. So let's hop over to here. Let's do we need to change this? Yes, we do, right? Edit the parameters. Let me find where they went. There, I see them over there. Yeah, we got to change these to 3 and to 126. And now we can do our right tail. And now down at the bottom right, we can put the 55.8. 55.8, click OK. And we get a p-value of 0. And just make sure that when you do this on your homework that you, again, attach that p-value 0 so we can reject the null hypothesis and say that there is enough evidence, or you could say strong since the p-value is so small, to support that. Now we're going to go with the alternative that the average height differs between at least 2 voice groups. Just to get back some of the context. But yeah, but definitely, yeah, this was not a fluke that if you were to look maybe at another singing group and you were to compare the average height for those that are in the soprano, alto, going to be probably much lower than those that are over in the bass, which tends to be like your deeper voiced male singers. All right, but that is the end of this recording. Hope it helps. Take care.